Hello, this is Camus Rocketry, Dark Team 221495. Today we'll be going over the basics of rocketry. So in our presentation, we'll have rocket science, a brief open rocket tutorial, and some things about 3D printing as well. So the general model rocket anatomy with regards to a payload rocket is displayed in the diagram on your screen. So starting from the left, we have our fins and our motor mount is mounted in between them. We also have centering rings, which keep our motor mount centered inside of the body tube of the rocket. We have a shock cord, which holds the parachute and tethers it to the rest of the rocket body so that it doesn't fly away. We also have altimeters in our altimeter bay, which are separated from the hot gases from the motor by the tube coupler and the bulkhead in the center of the rocket. And if we are carrying eggs, we will carry them above the altimeter in the payload section of our body. And then at the very tip of the rocket, we have our nose cone. So for some rocket parts. So one of the designs for the nose cone include the cone, the spherically blunted cone, the biconic section, the tangent ogive, the elliptical, and the parabolic shaped cones. Typically in rocketry, especially for egg lofting purposes, we use the tangent ogive or the elliptical cones. Typically things such as straight up cones or spherically blunted cones or even biconic shapes are used for aesthetic reasons rather than for any particular aerodynamic benefit. The benefit of using tangent ogive cones is that they have less drag separation in terms of their laminar flows. And so this basically means that when the rocket is traveling through the air, it will create less turbulence, and therefore it will be less drag inducing. That equation you see on your screen there is the equation for generating the curve for the tangent ogive cone. So that is the curve running from the vertex of the shape to its base. And so it's a function of the cone's radius, its length, and yeah. So the main body of our rockets are called the body tubes. They are made from reinforced paper tubes, fiberglass, and also can be 3D printed. Paper tubes is kind of the standard material for model rockets. That's the kind you get when you buy kits from stores, and that's the type that most people work with. The benefits of using paper tubing are that they are relatively durable. They're simple to work with, they're easy to work with, and they are very light. Fiberglass is typically used for high power rocketry because of the massive amount of forces that are usually involved with that kind of power. And fiberglass is a lot stronger than paper because it doesn't crumple like paper does. But fiberglass is more difficult to work with. It requires special equipment since you can't just cut it with a knife, and it has a tendency to be more expensive as well. 3D printed body tubes can also be used. They're basically just plastic tubes that you are able to customize easily to whatever shape and size that you want. And that's kind of the main benefit of it, is that you get to put your own designs into these tubes, whereas with paper and fiberglass, you kind of have a set foundation with what you're working with, and then whatever you want to add has to be tacked on top of it. So for terminology, this is mainly for paper tubes. We have BT 20, 50, 55, 60, 70, and 80. These are our general tube sizes for model rockets, and there is a corresponding size chart in the screen, in the diagram on the right side of the screen. And the numbers don't necessarily correlate with any particular measurement. So it's not like 50 is 5 centimeters or 5 millimeters, but they do increase in size given increase in terminology number. So one of the most important things about competition rocketry, at least, is determining altitude in an accurate way. So the American Rocketry Challenge regulates which altimeters we can use. And all three of the models that we can use are barometrically based altimeters. So basically the Perfect Flight Peanut, APRA, and the Firefly all detect the pressure of the air at the ground and detect the pressure in the air at the peak of the rocket's flight, and thus we'll be able to determine how high the rocket flew, judging from the difference in the temperature between its apogee and the ground. So the phases of flight are shown in the diagram on the left of your screen. So first we have liftoff, and then the rocket accelerates for the period where its motor is burning. And then it reaches its climb phase, which is after the motor finishes burning and it's basically just coasting now. And then at the peak of its flight, or in other words, its apogee, the motor fires an ejection charge and the parachute is ejected. And usually the rocket or the nose cone is shoved out as well. And this is typically connected to the rest of the rocket by a shock cord, which is usually a elastic cord of some sort, of some length. And this just keeps the rocket all together and prevents it from being shot out in 5 different directions. So after that, the parachute deploys, and then the rocket drifts down to the ground, hopefully in one piece. And here's a video of a much larger rocket, but doing, fundamentally speaking, the same stuff in the diagram. And so the rocket has just ejected. And especially for this type of rocket, the sections actually separate from each other and descend on their own parachutes because it is such a large vehicle. So there you can see that the main parachute has deployed. And so that is a demonstration of the phases of flight of a rocket. So you might be wondering how a rocket is powered. After all, there is not there's not a car engine in the back. So for traditional model rockets, it is powered using a black powder motor. So basically it's a propellant that's loaded into a paper casing, and this is not say lit on fire, but it is ignited using an electrical charge, and then this burns, and this burn provides thrust to the rocket and thus pushes it into the sky. There are also other kinds of model rocket motors, such as ones powered by ammonium perchlorate. These are usually termed as composite motors and tend to be more powerful, like F-class motors that usually are used for egg lofting, and mid-power launches typically have this kind of chemical compound in them. And then there are also reloadable motors, which allow you to reuse the outside casing. And basically you just, instead of buying new motors every time, you only buy the propellant and then you put the motor together yourself, thus saving cost, but also, that makes for more margin of error because you're the one putting the thing together rather than the manufacturer. So how we classify rocket motors is through a quarter or an eighth A to an O motor scale. And so from 1/8 A to O, it goes from really weak, shall we say, to very powerful. The most powerful of which can take a rocket into what is basically the scientific consensus of space. So these are very big rockets that can fly very fast and can be like 30 feet tall. And so these are very big rockets. But typically, the type that you'll be flying and that the type that we fly are categorized in the low to mid power range. So that's from 1/8 A to, say, an F motor. And these rockets are accessible to most people because they don't have any legal restriction as to who can buy them. And so we can basically purchase them and launch them if we have a big enough field. But motors that are bigger than an F class require special certification. So these are what are usually known as level 1, level 2, and level 3 high power certification. And you need to get certified from the National Association of Rocketry or the IEEE Rocketry Association. So that's the two governing bodies of national rocketry. And basically you have to demonstrate that you know how to build a rocket that is safe for that kind of power. Since if you build, say, an A-class motor or an A-class rocket and something goes wrong, not much is going to happen in terms of damage. But if you have a rocket that has the potential to reach 40,000 feet and that ends up going sideways, then that can be quite a dangerous thing. So as long as we stay in the model rocket arena, and we have pretty much a lot of leeway on what we can do in terms of our design. So in terms of designation, as you can see in the diagram on your right, an example of a motor is a C6-4. So the C tells you basically what class it's in. So you know it's a C-class motor, meaning that it's going to be within 5 to 10 Newton seconds worth of impulse. And then the 6, so that's the second, well, that's the first number, and the second character, I suppose, is the average thrust that the motor is going to give you. We're going to explain average thrust in a bit. And then the last number is the delay time. So that's the amount of time that passes after the motor finishes burning and the time that the parachute is ejected. So sometimes this can be 6 seconds, sometimes this can be 8 seconds, and sometimes you get to modify how much the delay time is in a reloadable motor. So that's kind of a modifiable thing that you can do. So this has already been partially touched on, but there's two different types of model rocket engines. So the first one is black powder, and it is, as its name suggests, filled with black powder. It is manufactured by Estes and is usually used from an 8E class motor. So these are smaller motors that are used. And one of the reasons that they are typically relegated to smaller classes is that it's, legally speaking, a bit harder to sell massive tubes of what is basically safer gunpowder. And so that's why we have composites, which are chemically based ammonium perchlorates, and these are usually manufactured by Aerotech and Cesaroni and can be found in all motor classes greater than F. And so these are, legally speaking, easier to deal with because they are safer in some regards. And they come in single-use and reloadable options. The single-use benefit being that they are easy to use. You put one in to the rocket, you launch it, and then after the launch, you take it out, throw it away, and then you put a new one in. The downside is that they have a tendency to be a bit cheaper, a bit more expensive rather, by $1 or $2, depending on where you buy your motors. But that's kind of a personal preference as to whether you value easy to use or more affordable. But the reloadable ones are cheaper, and you get to control the delay, which may be desirable for some people depending on their rocket's design and what they are trying to do. And reloadable ones, you get to put the motor together yourself, which can be, to some people, fun, and to others that may be kind of a drag, because then you get to launch less because you have to take time and clean out your casings, and then you also have to make sure that you put it all together correctly, because reloadable motors have not to say a tendency, but they are known to explode if the launcher does not do it correctly. So that's one of the downsides of reloadable motors, but they are cheaper. So motors have a thrust to weight ratio, and this is important because this affects the stability of the flight. So if we think about it, the motor's thrust, shall we say, the maximum thrust is kind of like the horsepower in a car. The higher the max thrust is, usually the faster it's going to accelerate to its maximum speed. So in a car, if you have high horsepower, you can accelerate a lot faster. Your maximum speed is still going to be, relatively the same, but you will get to that speed a lot faster. And so in rocketry, the minimum thrust to weight ratio is 5:1. So that means that the maximum thrust of the motor that you're choosing over the mass of the loaded rocket should be at least 5:1. That's a minimum safety standard. Once you get lower than that, then once there's wind or if there's any other flight instability, then your rocket does have the chance of having not very good things happen to it. And having higher thrust to weight ratios also means that you're going to fly straighter, and that things in the air that can affect the direction of the flight, like wind or a wind gust or any air currents, are going to affect it less because there is less time for those forces to be acting on the rocket as it is traveling upwards, because it is getting to where it is getting to the flight's peak a lot faster than a slower burn rocket. So the talk about stability in a rocket brings us to the stability margin. And this is the measurement of, this is the distance between center of gravity and the center of pressure, which is measured in the units of calibers, which is basically the diameter of the rocket. So if I have a diameter of a rocket that is 2 inches, and then the distance between my center of gravity and center of pressure is 4 inches, then I will have a calibers of stability of 2. So that's 2 stability margins, or 2 calibers. And 2 is usually the minimum that we like to go for. So that is the nominal number for a stable flight for a generic model rocket. And so this means that when wind pushes on the fins, the rocket has sufficient counteracting force to readjust its direction and continue going in a straight direction. Once we get below 2, and especially below 1, you never want to be below 1. If you're in 1.5 territory, in theory, you should be okay. But once you get below 1, then your rocket will no longer be counteracting the forces such as wind, and instead will be compounding those forces. So instead of readjusting the nose cone to go straight, your nose cone will follow the wind, and therefore it will be blown over, so to speak. But there's also a maximum to the calibers of stability that you want your rocket to have. And this number isn't really a set in stone sort of number, because it will differ based on the kind of rocket that you are flying. So some rockets can have a higher tolerance for calibers of stability, but some may have lower ones. And so the bad thing about having too high of a caliber of stability is that it will overcompensate too much. And so if we think of the rocket, looking at this diagram, as kind of a seesawing object rotating around the center of gravity, the fins will swing left and right based on the kind of forces that are acting on it. And so if we have a nominal calibers of stability of 2, then the fins will swing back into a vertical position relatively quickly. But if we have too great of a stability margin, like say we have one of 10, for example, then the fins will continue swinging back and forth, because it will continue to overcompensate for the difference that it has from vertical. And so that can mean your flight will go lower, and it means that you're going to have more forces that have the potential to rip your rocket apart. So stability of a model rocket is very important from a safety standpoint, because it can mean, the difference between whether your rocket's going to go straight or whether it's going to, point the wrong way. So for OpenRocket, OpenRocket is the simulation software that we use for designing model rockets. And so this allows you to input components that we talked about in this presentation, and you get to specify, what model you want, what size, what shape even, and see how high it will fly given whatever kind of motor that you decide to put into it. And so you can simulate all of these things and make adjustments accordingly and see whether they are safe to fly by looking at the stability margin that it calculates and it tells you. And so this saves you some time, it saves you some money from flying a rocket that isn't actually safe to fly. And it's also really fun to use. And most importantly, it's also free. So it's very accessible to everyone. And now your goal for today is to design a model rocket that can send a 30-gram payload to 400 feet using BT-60 and BT-50 diameter body tubes. So one of the important things to note in there is that there's an altitude target. And so you have to know how to modify the rocket to make it go lower, make it go higher. Sometimes you can add weight. Other times you can modify the shape of the rocket, or maybe how big the rocket is. Or maybe you could modify the kind of motor that it uses. But that's all up to you. So I'll leave that for you to do. So thank you for listening to this presentation brought to you by Canvas Rocketry. I hope you found it very helpful, and I encourage you to visit our website at canvasrocketry.com. On our website, you can find more about our club at the school. And you can also view launch photos and videos from this past season of our small and big rockets as well. And if you have any questions, there is a comment section on our website, and we hope to hear from you soon. And thank you for listening.